Greetings, aspiring scientists. Welcome to my video today on covalent networks and giant covalent structures. So it is actually Christmas today, December 25th. Didn't think I'd be making a chemistry IB YouTube video on this day, but in Japan it's just a normal day where I live, so most of the people I know just went to work normally, so I figured I'd do some work too. So we are actually going back a unit. We were doing 2.2.8, just finished talking about intermolecular forces. So I'm going to 2.2.7 now. Can't forget this one, you gotta go back. I just think it was better to study intermolecular forces first before we do this. But covalent networks are definitely important as well. Let's go to my slides. So covalent network structures. First we have to learn about something called allotropes. Maybe the first time you've heard this word. What are allotropes? These are different bonding structures of the same element or compound. And specifically, we're talking about different bonding structures at the same temperature and pressure. Same temperature and pressure. That's important because if you think about something like water, yeah, of course there's liquid water, solid water, ice, gas, water, vapor. But all of those happen at different temperatures at standard pressure here on the surface of Earth. But there are some compounds and elements which can form different stable bonding structures just at room temperature and pressure, or any other temperature and pressure, but usually we're talking about standard. So what are some examples of pure elements that can take different forms at the same temperature and pressure? So the one that's commonly used is carbon. You guys probably know that there are many different types of carbon. There's like diamonds, a very strong structure, stable, versus like graphite in your pencils. That's a different bonding structure, different properties. Okay, let's move on. So, probably the most famous group of allotropes are the carbon allotropes. Different allotropes are often formed through covalent networks, giant covalent structures. So these are similar to ionic bonding that we've studied in some sense, where you have what can be considered a repeating unit. And you can just copy and paste those bonds and atoms over and over and over, millions of trillions of times to get the actual solid that you might find in the world. So carbon has maybe 3 main allotropes and some other variations of these. I'll go through more than 3. So what do we have? Here are some examples. I got this from a Journal of Material Chemistry, I think. Some good visualizations of some of these. So the ones I want to focus on first are diamond, that's the bottom right. So diamond has carbon bonded to 4 other carbons. Every carbon is bonded to 4 other carbons, and they are bonded through a tetrahedral molecular geometry. Although they are not molecules, the geometry is still tetrahedral. Carbon forming 4 bonds, and nothing else really in this structure, although you might have some impurities in real diamonds. The base structure matrix is just carbons tetrahedrally bonded to other carbons. So although this is a 2D image, you can imagine the actual structure is 3-dimensional because tetrahedral structures are 3-dimensional. So we know carbon can form 2 bonds in the same plane, one coming out, one going in. So this kind of structure repeats over and over and over. Each of these carbons will form 4 bonds, to other carbons. And that's our diamond structure. That repeats over and over and over. Another one of the main allotropes is graphene. That's C on this image. So it's like a bunch of hexagons, and it's flat. These carbons are trigonal planar. Okay, so what they actually have is at least one double bond and then 2 single bonds. This gives them 3 electron domains while maintaining the 4 bonds that carbon forms. And it causes the whole graphene structure to be flat. What else do we have? So we have E is graphite, but graphite is just graphene, but many layers stacked on top of each other. So these layers are basically just graphene, flat, trigonoplanar carbons, hexagons. What else do we have? We've got the carbon nanotube, or any type of nanostructure you might hear of. There's nanotubes, nano walls, nano tools, whatever. Basically, they are all formed with the same structure, which is, again, graphene. You can kind of see that there. The hexagons as you look straight through the tube. But it is a flat structure that has been just curled around and folded together. So those carbons are also trigonal planar with 3 domains but 4 bonds, 1 double bond per carbon. What else? We've got fullerene. This is actually a unique one. This is not a covalent network. It's not a giant network, despite the fact that this unit is labeled as giant covalent networks. This one is a molecule. It is 60 carbons, C60, all bonded together in a kind of soccer ball shape. It's pentagons aligned with hexagons to make a kind of sphere, but really it is a specific mathematical geometry. I forget the name of the structure, but the soccer ball shape, we model our soccer balls after that shape as well. It's called fullerene or Buckminster fullerene, or sometimes Bucky balls, after I think the scientists who mainly worked on it. So this is also an allotrope, even though it's not a giant network. It is a way that carbon at standard temperature and pressure can bond with itself to exist stably, and it is quite stable. So the last one I didn't mention is amorphous carbon, and it looks kind of like just a mess, because it is a mess. I think this is just random bonds. You could have single bonds, you could have a double bond, you could have a radical, just all sorts of things, maybe a tetrahedral one. And these kind of just continue. But all these carbons should have either 4 bonds or like non-bonding electrons. You could have all sorts of things just in a mess, and this is why it's not very strong or stable. But it is a way when carbon is formed sort of quickly, I think, like in soot or charcoal, that we might have amorphous carbon forming. So these are the types I would recommend you learn about. There are other ones and other specific variations of these structures, but I think for IB chemistry, this is probably enough. So I just want to go through a little bit more about the graphite-graphene flat structure. So every carbon has 1 double bond and 2 single bonds, so we can kind of get this structure. I've got a bunch of sheets here, so if you imagine just one of these flat sheets, that's a graphene. It goes on sort of indefinitely in all directions. But as we stack 1 or 2 or 3 or many of these layers together, we get what we would call graphite. So the red ones you can consider the double bond. And then each carbon also has 2 black bonds, or gray. So it's quite interesting. It's very flat, and it's formed with hexagons, and it's got alternating double and single bonds. So the important thing, one thing about this, is that double bonds on every carbon in this structure means that there's kind of a highway created. Maybe I can draw this a little bit. So if you've got these carbons, and every single one has at least one double bond. This kind of arrangement, double, single, double, single, double, single, creates a pathway where the double bonded electrons are able to travel onto any carbon in that structure. And since every carbon on a sheet is connected in this way, it means that electrons can travel anywhere on this sheet, which is very interesting. So we call these delocalized electrons. This is in comparison to localized at one particular carbon for their entire lifetime. It's not the case here. They are delocalized, D meaning not. So this allows the sheets to conduct electricity because we need mobile charge carriers, moving charged particles, and through the graphene sheets, we can have that. So very interesting structure. Let's take a closer look at C60 Fullerene. So Buckminster Fullerene is a carbon compound which is in the shape of a soccer ball. It's alternating pentagons and hexagons, or rather one pentagon surrounded by 5 hexagons, I think is how it works. So these create a kind of sphere shape. These can actually be used to capture and transport atoms or molecules inside. I've seen some papers describing such transport structures. I don't have a good picture of that right now, but I do have just a 3D model of the fullerene, and I'll rotate it around a little bit so you can see it is very much like a soccer ball. Quite interesting. So there's slightly different bond angles in this, in the hexagons and pentagons, but they are just stable enough to form an overall stable structure. Okay, let's move on. So carbon is the main one that we study in IB here, but there are other networks, of course. One of the most common ones is silicon, especially silicon with oxygen. So here's just some data to compare. Carbon in the graphite form has an atomic radius 75 picometers, whereas silicon 114. So why would we care about that? Well, we can compare that with the enthalpy, the bond energy, and see if it follows what we know about enthalpy and radius trends. So the bond enthalpy of graphite is 346 kilojoule per mole. Fairly average. Silicon 226 though, quite a bit lower, less stable. And so generally the shorter bonds have the higher enthalpy. So that kind of follows here with the radius. Carbon having smaller radius in graphite goes with its higher enthalpy, whereas silicon having longer goes with its lower enthalpy. They're kind of farther away. Melting point, graphite, very high, 3,500 Celsius, whereas silicon about half that, or less than half, 1,414. Again, probably due to their silicon's lower bond enthalpy there. Boiling point, very similar, much higher for graphite, slightly lower for silicon. First, ionization energy. So I think this doesn't really have to do with graphite, but it's just how much would it take to remove one electron from a carbon atom. It's 1,086, whereas silicon 787, quite a bit less. Again, that is due to shielding, being in a lower period, less effective nuclear charge felt on the outer electrons in silicon. But then there's something interesting. We could compare the bonding with oxygen. So the CO bond, carbon oxygen, versus the silicon O bond, silicon oxygen. It's actually much stronger in silicon, 466 versus 358. And I think the reason that it's good to show you this is that silicon, I think, can form a pure, solid kind of network, but much more often on Earth here. Silicon has had longer time to mix with other elements and be oxidized. So we're much more likely to find silicon oxide, so silicon dioxide on Earth here. bond enthalpies are more stable, and the network that it forms is more stable. So here's kind of an image of what the network looks like. So the kind of beige large atoms are the silicon, and the red ones, slightly smaller, are oxygen. I want you to ignore the white balls. Those are hydrogen. I just couldn't remove them from the structure. But what actually will happen is that the oxygen will connect to another silicon and repeat the unit that I'm showing here on this slide. So instead of these white balls, instead we'll get another one of this whole structure that I'm showing you here. And those will be connected over and over as a repeating unit. So we can just take a look at this quickly if I can play the video. Or the animation. So it's a very interesting 3D kind of structure filled with tetrahedral silicon atoms connected by oxygen. So each silicon is bonded to 4 oxygens. Remember, silicon has very similar structure to carbon. It's got to form 4 bonds to get its octet. But oxygen only needs to form 2. It's also got 2 lone pairs on there. So this is just the way that the structure works and the way that this becomes the repeating unit. Silicon must form 4 bonds. It forms them more strongly with oxygen than itself, so it bonds with oxygen in every position. And then oxygen will bond with 2 silicon atoms. Okay, so oxygen connects 2 silicon atoms, silicon bonds with 4 oxygens, and then this unit will repeat, and instead of these white hydrogens, it will connect with another unit of this kind of shape. So what else can we say? The SiO bond is particularly strong. This makes up a large part of Earth's crust in the form of rock, quartz, sand. Sand is just small grains of a bunch of minerals, right? Quartz is the main one. So this is SiO2. You can actually just repeat the SiO2 unit as the kind of copy and pasted thing to generate this whole structure. And we know this, I think, mainly as quartz. So what are some properties of networks such as these? Generally, they do not conduct electricity. Things like diamond, silicon dioxide do not conduct electricity, but if there are delocalized electrons, for example, in graphite, graphene, there will be some conductivity. I think even amorphous carbon has much better conductivity than diamond because there are fairly often double or triple bonds in the amorphous carbon random structure that help it conduct. Okay, covalent networks have higher melting points, or rather high melting points, higher than normal molecules, we can say. Normal molecules, covalent molecules like water, ammonia, hexane, whatever, they rely on intermolecular forces to generate their boiling and melting properties, right? But networks, if you want to boil or melt a network, you have to destroy it. And so it's kind of the strength of the network that becomes the boiling point and melting point, which is very high. The networks are stable and strong. So covalent networks are usually strong and hard. There are some exceptions to this. Like you probably know, graphite is used in pencils, and it's fairly soft, right? As you drag your pencil lead over the page, it falls apart. And that's because you're ripping apart those layers. Those layers are not covalently bonded together. They're just stacked on top of each other. They're actually held together by probably intermolecular forces like London forces, which are easy to break just with some physical force. But things like diamond, quartz, obviously very high, strong materials. High-strength materials. Covalent networks do not dissolve in most solvents. So I think we've talked about dissolving like ionic compounds a little bit. The solvent molecules surround and apply intermolecular forces to parts of the crystal. But here, it's not going to happen. We've got covalent bonds, not ionic bonds. So ions can't be separated. We've got covalent bonds between non-metal atoms in these networks. Solvents just can't get in there. They can't break apart those bonds at all, so we cannot dissolve them most of the time. Even graphite or amorphous carbon. So let's do a little comparison here. Let's compare the conductivity of graphene with diamond with sufficient reasoning related to structure. So graphene will be able to conduct electricity quite well, very well I would say. It's because it is a long sheet of covalently bonded carbon atoms, and every carbon in that structure has at least one double bond. This creates delocalization across the whole structure. Any pair of double bonded electrons can go to any position by traveling across the kind of highway of delocalized electrons and double bonds. Diamond has no such structure. It is all single bonds, and they're locked in place, localized to between the carbons, forming the bonds that they exist in. So very, very low electrical conductivity for diamonds, probably one of the lowest that we know of. 2. Explain why diamond and silicon have higher boiling points than carbon dioxide. Carbon dioxide, obviously a very low boiling point. You probably very rarely seen dry ice that's very, very cold, like I think below minus 100 degrees, where carbon solidifies. But normally carbon dioxide is a lightweight, low London force, no permanent dipole molecule that would only be held together by intermolecular forces. The covalent bonds within it, carbon-oxygen double bond, only exists between the atoms in the structure, not as intermolecular forces, so its boiling point is low. Diamond and silicon dioxide, though, every atom in that forms multiple covalent bonds, and they are with the atoms adjacent to them, right next to them. So that forms a very strong, positional series of covalent bonds around each atom. And if you would want to move or separate one atom, you'd have to break several covalent bonds, rather than intermolecular forces such as in carbon dioxide. That's the key. Okay, so if you didn't follow what I just said, rewind and watch it again. I think it's very true. Comparing a network to a molecule is highly different. Molecules held together with intermolecular forces, networks held together through a series of strong covalent bonds, every single atom. Okay, then we have this kind of chart. Oops, don't want to give away the answers here too quickly. So you can think about how you would label each of these things in this green table, this little activity: diamond versus graphite versus graphene versus C60 versus silicon dioxide. So what are the elements in this? What are the arrangement of the atoms, the molecular geometry? What is the electrical conductivity? So you could try this if you like. Pause the video. If not, then I'll just give you the answers now. So what elements are in diamond? It's all carbon. I think I need a different color. Let's try red. Carbon. What's in graphite? Carbon. What's in graphene? Carbon. What's in C60? Carbon. What's in SiO2? Silicon and oxygen. What's the arrangement of atoms? The geometry is tetrahedral. Network structure. Graphite is trigonal planar. Each carbon has one double bond, two single bonds. Graphene is also trigonal planar. So what's the difference? It's just that graphite is multiple sheets. So we'll also include that here. Multiple sheets of graphene stacked with each other. Okay, C60. These are approximately trigonal planar as well. Each carbon will have two single, one double. but instead of a flat sheet, they form the soccer ball shape. Sorry for any European listeners or people who call it football instead. I'm calling it a soccer ball. I'm from Canada. Then SiO2. So the arrangement here is also tetrahedral, similar to diamond, especially on each silicon. The molecular geometry is tetrahedral. For the oxygens, I think it will be bent actual geometry. They still have the lone pairs on there. Electrical conductivity, then, diamond, very low. No mobile charge carriers, probably similar to solid ionic compounds. Graphite, I think high. Along the sheets, electricity is conducted very well, but I think compared to graphene, a single totally connected sheet, it's not quite as high, although I don't have real data for this. But you can imagine one single completely connected sheet where every carbon is on the highway. That should have very high conductivity. With graphite, you probably have these sheets where everything's connected within the sheets, but the sheets are slightly separated. So every once in a while, to jump to a new sheet, an electron must make that jump, which is a little bit of trouble. To jump across that distance, I think, and continue conducting through the sheets. C60, low conductivity. And why is that? Even though it has trigonal planar and it has delocalized electrons within its structure, it's got every carbon having a double bond in that soccer ball shape. So electricity can conduct well within that soccer ball, but that's only 60 carbons within trillions and trillions and trillions in a particular real sample that you might have. To jump between the soccer balls would have to be a very difficult jump, I think. The soccer balls are molecules. Remember, C60 is not a network like most of the other things we're talking about today. It's a molecule, and so the molecules are held together by London forces, similar to the graphite sheets, but they're not stacked nearly as well. They're not held together closely, so the conductivity suffers because of that. SiO2, very low conductivity. No mobile charge carriers, no delocalized electrons. The electrons are locked in place in the covalent bonds between silicon and oxygen. So things like quartz, if you go get a quartz rock from outside, try to pass a current through it, I don't think you'll detect very much at all. It's an insulator. Okay, let's move on. That might be all I have today. I do just have one more summary slide, I think. So most of what I just said in that previous activity is also here. Diamond tetrahedral, graphite trigonal planar, graphene trigonal planar, C60 trigonal planar with some variations. Those bonds cannot be exactly 120 degrees as in a normal trigonal planar because you've got to form pentagons and hexagons and then slightly bend those inwards to get the soccer ball shape. Hybridization, this is an HL topic, but if you're curious, there's different types of hybridization in all of these. Diamond has sp3, while the rest have sp2, which is related to them being trigonal planar and tetrahedral. Bonding, diamond, graphite, graphene, these are covalent networks. C60 is a covalent molecule with 60 carbons only. Intermolecular forces, the first three, diamond, graphite, and graphene, do not have intermolecular forces because they are not molecules. However, there are still some forces that can hold together the graphite sheets. London forces, I think. And So that's the reason why when you slide your pencil across the paper, you can apply enough force to separate some of those layers, and chunks fall off onto your paper and become writing, right? C60 Fullerene has only London. There's no dipole or hydrogen bonding in that, but there can be quite strong London forces. So I think it is a solid at room temperature and pressure, because there's a lot of electrons and chances for dipoles and polarizability in such a large molecule. Conductivity, diamond, bad conductivity. Graphite, pretty high. Loose sheets can conduct electricity through delocalized electrons. Graphene, very high. You can imagine it as a bunch of connected sheets or just one large sheet. And bad conductivity in C60 Fullerene. They are molecules where there's not a clear pathway for electrons to travel or charged particles to conduct electricity. Finally, hardness of the solid. Diamond, very high. If you wanted to crack that or separate it, you would have to break many covalent bonds. Graphite, it's low because the sheets can slide and separate. They're only held together with London forces. Graphene, high hardness, although I don't have a good reference for this. I'm actually just kind of guessing. But you can imagine one sheet is actually very thin, so it might be difficult to crack or break that sheet. But it's not going to be a material that you can really work with in your hands. It's going to be like a thin layer on top of something. Then C60, low hardness of solid. You can break apart the London forces fairly easily in the solid form of C60. Alright, so that's all I have for today. Next time we'll get into sort of a final summary of the properties of covalent substances. And when we're done that, we can move on to metallic bonding, I think the last type. So thank you for listening. Hope you learned something. See you next time. Goodbye.